This is Calcium-41. It's a reference material, just like the thorium-230 or other radionuclides that we store in our nuclear lab. Even though it's radioactive, measuring this stuff is quite difficult, and this is part of the story of Calcium-41. So let's dive into the nuclear data. Calcium-41 has a half-life of 99,400 years. It decays into stable potassium-41 via electron capture. It does not undergo beta-plus decay because the Q value for its decay is only 421 kiloelectron volts. A Q value of at least 1022 kiloelectron volts is required for beta-plus decay. It decays from a 7/2 minus state directly into the 3/2 plus state. This is also the ground state, which means that no gamma lines are associated with this decay, making measurement rather complicated. It occurs naturally in trace amounts because it is a cosmogenic radionuclide. Some of it is produced via neutron capture of calcium-40. This is relevant for geochronology. However, we'll soon learn that the natural production of calcium-41 is quite a bit more complicated. In terms of naturally occurring traces, the natural isotopic ratio of calcium-41 to calcium-40 is between 5 times 10 to the power of minus 16 and 2 times 10 to the power of minus 14 to 1. Is that important? Yes, because it allows us to date rocks. For example, if the calcium-41 ratio is elevated, that means that this rock was exposed to a higher neutron flux, as calcium-41 could otherwise not have been formed. At such low concentrations and with such a long half-life, the decay radiation can't be used for detection. Instead, accelerator mass spectrometers are needed. We happen to have one here, which is why we also have this solution. AMS stands for Accelerated Mass Spectrometry, where isotopes are sorted by mass. Each radionuclide commonly used for dating has an issue with isobars. Nuclides with the same mass, which can interfere with the measurement and artificially elevate the 41 from calcium-41 peak. For the calcium-41 interference is potassium-41. In the spectrometer, potassium-41 can be suppressed by measuring the sample as a hydride. Now that we somehow know how to measure calcium-41, where is this measurement applied? For example, nuclear power plants. In our practical course, we work on determining calcium-41 content in nuclear power plant concrete. Concrete contains calcium-based compounds, like calcium hydroxide and calcium carbonate, which are exposed to a high neutron flux in a nuclear power plant. This exposure can produce calcium-41 from calcium-40. Given its long half-life, calcium-41 causes the concrete to remain radioactive pretty much indefinitely compared to human lifespans. AMS is used to determine whether the calcium-41 content is high enough to make disposal problematic or low enough to handle it as just regular concrete waste. I've mentioned that calcium-41 is produced via neutron capture. However, in space, where meteorites originate, there is no significant neutron flux, only high proton fluxes. These too can generate calcium-41 through a bit more complex nuclear reaction. What we are looking here is lunar soil number 12070. That's original material brought back from the Apollo 12 mission. Unlike Earth, the Moon lacks an atmosphere to moderate cosmic rays or generate secondary neutrons. Instead, protons strike the lunar surface directly. Processes we associate with atmospheric interaction occur directly within the lunar soil. In one study, they looked at some lunar basalt and determined its composition to have a relatively high titanium content, additionally to the normal iron, silicon, and aluminium. Calcium-41 can be produced on titanium isotopes via a P3PXN reaction. The X depends on the titanium isotope involved in the nuclear reaction. What happens there is similar to what happens during irradiation at the cyclotron. Solar cosmic rays with high energy bombard the Moon's surface. These protons decelerate and reach an energy optimum of 78.8 megaelectron volts at a depth of 0.08 grams per cubic centimeters, where calcium-48 can be produced. Below this depth, the proton energy decreases and so does the production of calcium-41. So right at the top, the protons have too much energy for said nuclear reaction, and then they are slowed down enough for this reaction, and after some more distance they are too low in energy. Every nuclear reaction has this kind of energy optimum. But to give you some context, 78.8 megaelectron volts is far outside the range of a normal cyclotron. They operate more up to the 30-ish megaelectron volt range. So looking at this reaction, we can see that neutrons are released, which means additionally reactions involving thermal neutrons further contribute to calcium-41 formation. This constant production, including spallation from elements like iron, allows scientists to model the proton flux on the moon. This is determined to be around 120 protons per square centimeters per second for energies above 10 MeV. Continuing in space, through these briefly mentioned spallation reactions that also produce calcium-41, we can detect calcium-41 in iron meteorites, even though they don't inherently contain calcium. However, I'm saving the topic of iron meteorites for another radionuclide. Since we are already diving into calcium radioisotopes, let me introduce to you two more relevant calcium isotopes. Calcium-45. This is a much shorter lived isotope. It's a beta-minus emitter with a half-life of 162 days, making it popular for studying calcium behavior in soil, for example. Since calcium plays an extremely significant role in biological organisms, calcium-45 is an excellent tracer for investigation of, for example, bone calcium and other metabolic processes. Simply search for 45 calcium on Google Scholar and you will find almost every calcium transport pathway has been studied using calcium-45. Caffeine and calcium interaction, yes, there have been studies with calcium-45. Vitamin D and calcium also studied with calcium-45. There are plenty of other applications to be found, just you search. The other isotope is calcium-48. Finally, we've come to the isotope beloved by many fans of transactinides. Calcium-48 isn't stable, but it's primordial. It's particularly stable as it's a double magic nucleus, with a magic proton number of 20 and a magic neutron number of 28. It's incredibly stable. Sure, calcium-40 is also a double magic nucleus, but with 8 additional neutrons, calcium-48 has a lower charge to mass ratio, which increases the likelihood of nuclear reactions producing transactinides. For example, calcium-48 was bombarded onto a Californium-249 target to produce organeson-294. I don't want to reveal too much here, as transactinides and other related topics will get their own video in the future. But here's a quick glimpse. During the production in 2002, a total of 2.5 times 10 to the power of 19 calcium-48 ions were accelerated with a kinetic energy of 245 MeV and bombarded onto Californium-249. This resulted in 2 observed events of element 118 production. This was according to Organeson's report on the first experiment. I hope you've learned something new about calcium isotopes. A special thanks goes to the Working Group of Analytics and Fundamental Nuclear Chemistry from Dr. Eric Strupp and the Division of Nuclear Chemistry at the University of Cologne, and to my Patreons. With that being said, thank you for your attention and goodbye!